Okay, let's get started. So, in case you guys haven't seen us around before, Abacus is an interchain communication protocol. And I'm going to give an overview of the protocol, but hopefully I'll be able to get quickly into kind of how you can build on top of Abacus and what tooling we have for developers. So, Abacus is, like I said, a platform for enabling interchain applications, and the kind of paradigm shift for dApp developers and smart contract developers is now your application state exists kind of across many different blockchains. And so there's no longer a single memory layout that contains all of your application state. It's kind of a shared state model. And so you might ask yourself, why would we be interested in doing this for smart contracts? And we kind of have like a few motivations for why this is a useful property. So for one, when I'm sure you guys are familiar with this problem, when you're setting out to deploy a smart contract application, you have to pick basically what blockchain you want to deploy on initially. And usually that choice involves some combination of what the user demographic is that you're targeting, what developer experience you'll have building the app, and kind of what risk you have in getting embedded within that platform. So if that platform eventually doesn't align with your interests as an application, you might be stuck, and it might be difficult to migrate away. And so bringing your application cross-chain really just means deploying on many chains. And with the kind of status quo of when applications do this, like you might have seen different DeFi applications in the ecosystem deploy on different blockchains over time because they wanted to reach a broader user demographic or maybe reach a platform where fees were lower, or that sort of thing. They tend to deploy those systems as separate instances. And so there's no shared state model. Basically, the new deployment on Polygon or Optimism is kind of like a singleton instance of their application with an entirely distinct set of participants and incentives. And so what that leads to is basically a fragmentation of the network effects. And so kind of the canonical example that I think of, which demonstrates this problem, is when Uniswap wants to go and deploy their system on a new blockchain. In order to bootstrap the liquidity on that chain and actually make their application useful, they have to go and deploy a new set of liquidity incentives to get people to initially become LPs for that chain. And so each time they do that, they're basically fragmenting their network effect. And the LPs within the ecosystem tend to be fairly mercenary. We call it like mercenary capital. And so they just chase these liquidity incentives. And so there's not really a stickiness to those network effects. Like basically the LPs are just chasing wherever the liquidity incentives are highest, which maybe is hard for the application developer to manage across a bunch of different chains. And so the idea behind Abacus is to basically eliminate that choice for developers and allow them to still only write their systems once, so like have a single set of smart contracts, but actually have this shared state model where you deploy on many chains, but you don't fragment your network effects, and you actually have like a unified network and a global set of participants. So there's like no distinction between the user on Polygon and the user on mainnet Ethereum, or very little distinction. And so there's no, Abacus isn't a blockchain itself. It's just rather like a very lightweight networking layer that sits between blockchains. And it allows smart contracts to communicate with each other across network boundaries. And so this also enables some amount of composability, which is kind of prevented by the like single VM model that most of us have been working in thus far. And so you can imagine actually not only your own app interacting with users on other chains, but your own app interacting with apps on other chains. And the benefit to your users and kind of the user experience that you create for your customers is you don't have to force your users to come to your chain and go through kind of a high overhead, both like cognitive and also like financial process of bridging their assets to your chain, maybe coming up with a new custody solution. And yeah, you're not locked into a single chain anymore. You're not beholden to like maybe the foundation on that chain. You can kind of like hedge your bets a little bit on maybe who you think will win the scalability wars. These sorts of questions that right now are really difficult to make a well-informed decision about. So the basic architecture, and I have some diagrams coming up, so we can move over this quickly, but the way it works is there's basically mailboxes. So if you think in like the traditional mailing system, you can put mail into the mailbox and you can take mail out of the mailbox. And so from the perspective of the smart contract API, that's all that's going on. There's mailboxes on every chain, and you can put mail into the outbox on a chain and tell it what the destination address is. So that's like in addition to what you're used to of like a smart contract address that you might make a call to, you also provide basically a target blockchain identifier as the destination, and then the Abacus system will go and basically relay that message to the inbox on the target blockchain, which is another smart contract, and will basically deliver that mail from the inbox to whatever the recipient smart contract that you specified on that target blockchain. Hi.
How are you?
Good. How are you? We're talking about Abacus.
Okay, that sounds good. So do you need the room in general for how long?
I'm not sure. I think there's a schedule outside.
So this is this one. Okay.
Yep.
Thank you.
And so, yeah, the system is fairly simple from an API perspective. There's mailboxes. Hopefully that's a familiar kind of analogy for people. But the, I guess, distributed system, which makes this possible, is a kind of proof-of-stake validator set. And so we're trying to take a more permissionless approach to these sorts of interchain message relays than maybe some other projects in the space. But yeah, the basic premise is when you put mail in the outbox, that mail is actually kind of committed to by a Merkle tree. And these validators, which are conducting the message relay between the different networks, are kind of constantly signing new roots or new commitments to the content of that Merkle tree in the outbox. And on the receiving chain's side of things, in order for a message to be processed from the inbox, there needs to be a quorum of validator signatures attached to a Merkle root, which commits to that message content. So this should be like somewhat illustrative. Sorry for the kind of pretty poor diagramming, but yeah, basic premise, Abacus sits between blockchains. It's not a blockchain itself, but you can, as an application developer, deploy your application across many chains and use this mailbox API to kind of like pass arbitrary messages between your application. So I want to jump into kind of how you can build on top of this system. And we have a few different layers of tooling that you can leverage as kind of a smart contract developer or a really a dApp developer. And hopefully this kind of like experience will be as familiar as possible to designing a dApp in a single chain context. That was the goal with building all of this tooling, is basically introduce as little like cognitive overhead to the developer's experience for going cross-chain. So we're going to talk about kind of like the tooling at the smart contracts layer itself, and then we can move into some of the kind of more peripheral tooling we've built out at the application layer, and then maybe walk through some examples and demos. So I think I've talked about this at length at this point, but basically there's an outbox contract on every blockchain, and there's this function on it called dispatch. And so in addition to passing a recipient address on the target blockchain of what contract you want to receive your message, you pass the blockchain identifier. That's just a uint32. We have a kind of like enumeration of all of the different blockchain IDs in our docs. Yeah, conversely, in order to receive a message on a blockchain from the Abacus system, you just have to implement this this interface that we call iMessageRecipient, which includes this handle function. And when the inbox contract processes a message, it will call the handle function on your contract. And so from the developer's perspective, there's just basically like two endpoints that they really need to understand. And then everything else is contained within their own system. So with respect to kind of libraries that we provide, we have two smart contract NPM packages that you can use. So we have the Abacus Network Core package, which basically publishes all of the smart contracts that are needed to enable this core protocol of basically this mailbox system. In order to basically know where the addresses are of these mailboxes on each chain, we have a contract called the Abacus Connection Manager. Basically manages a registry of addresses for the local chain's outbox contract, as well as all of the inboxes which correspond to the remote Abacus-supported chains. And the reason why this exists is because we don't want to enforce any specific deployment of the Abacus protocol, and so actually someone else can go and deploy their own instance and just use a different registry. But obviously we operate one of these for our deployment, and whenever we change the outbox or inbox interface, which are upgradable, and we deploy new mailboxes, we'll basically deploy a new connection manager to bundle the new version as a single address for kind of application consumption. And then on the kind of like client side of things, so if the connection manager is kind of like your API into the core Abacus system, the connection client is kind of this wrapper around the connection manager that smart contracts can inherit from, which basically gives them some nice utility functions on the outbox and on permissioning message delivery via this only inbox modifier, basically. And that uses a familiar kind of like Open Zeppelin ownable access control paradigm. And so the Abacus connection manager address, which is in that connection client that your smart contracts will inherit from, has like only owner access control for setting it. And so you can imagine in like the long tail of your application, that can be owned by a DAO that's doing token voting, and the DAO can decide when it wants to maybe upgrade to a new deployment of the Abacus system. So we don't kind of enforce any specific upgrade strategy for applications. And so then, I guess, getting into kind of the types of application architectures that we think are conducive to building on Abacus is something we call the router pattern. So I think we've kind of concluded as a team that one benefit we've seen of the EVM's dominance within the developer ecosystem is that developers are familiar with a single smart contract syntax, and they only have to write their smart contracts once, but they can deploy those contracts to many blockchains with different kind of like security models or user demographics, network effects, et cetera. And so this kind of allows the whole ecosystem to iterate more quickly on kind of smart contract design without compromising on like the lessons learned from previous projects or previous deployments. You don't have to make any changes to the source code to deploy on a new blockchain. And so like that's an obvious benefit to the EVM's like I guess pervasiveness. But like I said before, when applications redeploy their contracts in a new blockchain, they tend to kind of fragment their network effects. And so we've built this, we've been developing this thing called the router pattern that we expect most of our developers to consume or inherit from, which kind of leans into this EVM chain interoperability idea. And so the reason why it's called the router pattern is if you have a background in traditional networking, routers are these pieces of hardware that have these like static routing tables that define routing policies to forward internet traffic that they're receiving on the network with according to some knowledge of the network topology. So we use IP addresses to kind of explain the network topology to routers, but the Abacus router smart contracts are not too dissimilar from that mental model in that they're made aware of the network topology through the addresses of instances on other chains. And so basically, the router smart contract has a routing table within its storage, which basically defines how messages should be routed through a application. And so this kind of allows your smart contracts to send messages directly to your smart contracts on other chains without needing to specifically provide an address in that call, because the router kind of abstraction can handle that routing for you. And in addition to kind of handling the so you'll see here like the dispatch function on the router abstract contract is different from the one we saw earlier. So on the outbox, this is kind of like the lowest level API. There's the destination chain, the recipient address on that chain, and then the arbitrary message content. If you choose to use the router pattern, which is just a Solidity contract you can inherit from, you now get access to this internal dispatch function, which only has a destination chain and the arbitrary message to pass. And then conversely, you have to implement this internal handle function, which takes an origin chain, the sender address on that origin chain, and the message content and does some, logic within your contract. And so what's nice about this pattern is both of these functions are internal, so the developer doesn't need to think about basically cross-chain access control. All they have to think about is the access control paradigms that they're familiar with, which are like calls from a single chain context. And so they can use the same sorts of like libraries that OpenZeppelin provides, for example, without much overhead from the Abacus system. And we kind of handle the access control using this router table. So basically, if you choose to inherit from the router mixing contract, you basically can reject messages which are sent from untrusted remote contracts that aren't kind of included in this routing table. The kind of extension to traditional networking routers here is that because these routing policies are implemented in smart contracts, they can be arbitrarily complex. And so something that I'm personally excited about and have spent a lot of time thinking about in the past are these things called software-defined networks. Basically allows routers to kind of have like a more sophisticated routing policy than just a simple like network topology map, which might be application aware and kind of optimize the routing strategy based on some understanding of like a optimal application outcome. And so like one use case for this might be basically a gas price minimization routing policy for Abacus applications. So you can imagine as a developer, you get access to this API where if you're inheriting from the router, you just say, I don't care which chain this transaction or message gets processed on, but I'm going to send this message to the chain where the gas price over the past 100 blocks or 10 blocks is the lowest on average. And that basically allows you to offload computation and kind of like arbitrarily complex policy, basically. And if you combine that type of system with like a governance protocol, you get a framework for decentralized software-defined networks, which I think is like super exciting. So anyway, that was a bit of a tangent, but let's move on to, I guess, so this is kind of most of the smart contract tooling that we provide and library code. So just to summarize quickly, your contracts will either inherit from the connection client or the router, which already kind of handles the connection client inheritance for you. So the router is probably the highest layer abstraction that we provide so far. But we're continuing to think about what types of patterns and abstractions developers will find useful. If you're looking to get started writing an Abacus contract, this is probably the place to start inheriting from router. So I'm going to quickly move on to the, I guess, application SDK. Oh, and just quickly, excuse me. We have a hard hat plugin, which basically facilitates testing framework for our contract developers that will deploy a mocked version of the core system. So it'll deploy a mocked version of these outboxes and inboxes that doesn't basically require third-party validators to be signing messages like on your local hard hat node. It's just there's a stub function called process messages, and that simulates what would be happening in the distributed system. But yeah, so on the application side of things, we've again kind of leaned into the Ethereum ecosystem and just basically built extensions to libraries that we think most developers are already using. And so probably you guys are familiar with ethers. We have like the only difference between the Ethers provider and the Abacus provider is that now instead of having kind of a single like JSON RPC provider for a specific blockchain, you have a mapping from, the blockchain identifier to the provider for that network. And so we call this a multi-provider. There's a few kind of like configuration options, that different networks might have kind of different desirable properties. And so like one thing we do with this tooling is on Polygon, because some of our systems need to be reorg safe, we basically have this confirmations config that allows us to kind of hook into the same Ethers provider API, but make sure that we've waited for 10 block confirmations before we kind of proceed with the assumption that this transaction has been included in the canonical chain. So yeah, Ethers provider, I'm sure you're familiar with. Here's the hard hat plugin. Basically, there's this test version of the Abacus system that you can deploy against your hard hat node, and here's the stubbed method I was describing. So in your testing, you can basically call your contracts.some function, which dispatches a message. And if you want to test kind of the recipient handling of that message, then in order to invoke that, in order for your message to be processable, you have to get this approval from the core protocol. And so I think earlier I described there's this quorum of validators that are participating in a proof of stake protocol. But from the testing perspective, we're just going to simulate all that out. So you can call this function, and then you can basically verify that the message on your recipient contract was actually received. Whether that's an event that you emit or it's a state change, is up to the developer. In addition to testing, we've provided some deployment tooling, which similarly has this goal of making the experience familiar to dApp developers that have experience in a single chain context. And so I think this is pretty illustrative. Basically, you just have to define the logic for deploying your contracts on a single chain, and this tooling takes care of basically all of the kind of cross-chain deployment. So as an example, if you are using the router pattern, all you have to do is define how your contracts are deployed, and then the router deployer will handle basically the population of the routing table that I was describing earlier. So you don't have to, again, think about any of these sort of system level distributed system concepts. And hopefully all of that can be abstracted away for you. So yeah, again, you just implement this single chain deployment function. It's abstract deploy contracts, and then our tooling will do kind of all of this additional initialization for you. And so again, the router is the highest layer abstraction. You would just inherit from this router deployer if you wanted to leverage this deployment tooling. Okay, so once our application is tested and it's deployed, finally we need to build some sort of application that allows users to interact with your system. And so we have this app abstraction, which basically manages collections of contracts that exist across chains. These are Ethers contracts, and basically this works well. This works nicely with the deployment tooling that we've provided, such that it kind of consumes artifacts generated by the deployment tooling. Deployment tooling will also go and verify your contracts across all the different block explorers. So yeah, I mean, these are just, obviously, because they're at the application layer, these are mostly all optional, but just wanted to walk through kind of some of the peripheral stuff we've built. But yeah, I think now that we're through some of the more dry stuff, it would be nice, because we're at a hackathon, to jump into some examples. So the first thing I want to look at together is an example of a cross-chain token. So I think this is the pattern that probably most people who have been thinking about like cross-chain are familiar with. Thus far, we've built out both a cross-chain ERC20 and a cross-chain 721. Hopefully this will be illustrative of like how simple it is to extend your application to be Abacus compatible, because all we're doing here is consuming kind of the readily available OpenZeppelin libraries for canonical implementations of tokens. So in this case, we're using the OpenZeppelin ERC20, and the only additional function endpoint that we have here that's an external function is this function transfer remote. And so we've just simply extended the ERC20 standard with one additional function that enables transfers to target remote blockchains. And the way this is implemented is basically when you initiate a cross-chain transfer, the token amount that you're trying to transfer is actually burned on the local chain. And this function call here is, I guess, like slightly out of date with the most recent API we're providing. But basically, you dispatch the message, which encodes the recipient address and the amount of the token that you want to send to them on that remote chain. And then we just emit an event just to kind of, for bookkeeping, if there's, yep.
Is the liquidity shared by the blockchain?
So there's actually no liquidity layer here. This is, I think, something that maybe is like a different approach to what you might have seen in traditional token bridges. And so traditional token bridges use what we call like a lock, mint, burn, unlock pattern. This specific implementation, I guess, of a cross-chain ERC20 has no locking or unlocking. So basically, instead of actually having like wrapped representations of tokens in remote contexts, you have no distinction. Your application like has no distinction between tokens which live on Polygon and tokens which live on Ethereum mainnet. It's, again, this like shared state model. And so like from your user's perspective, their balance is just the sum of their balances across all the chains. What this allows you to do is, like, depending on the context of their like interaction with your application, you can decide what routing policy you want to take based on like the action that they're interested in. But in any case, there's no liquidity layer here. Basically, we're just burning the tokens on the local chain, and once the message is processable on the destination chain, your handle function gets called by the inbox. Because we're inheriting from router, all we have to implement is this internal handle function, which is, again, nice because then we don't have to think about access control. The router pattern or the router abstraction handles kind of the access control through the routing table for us. And we decode the recipient address and amount that was sent to us, and then we mint that amount to the recipient address on the local chain. And so this has like maybe like I guess to elucidate the like distinction of this type of approach from traditional token bridges, what's nice about this is there's no kind of like canonical chain where all of the collateral exists. And so I think at the beginning of the presentation, I talked about kind of in a single chain context, when you're making the first decision of what blockchain you want to deploy on, you take on this risk of like this embedding effect of the platform that you're deploying on. And typically your token exists in that blockchain, and it's very difficult for you to actually migrate away from that chain because that's where your token is, that's where your users are. It's almost like we're kind of regressing back into like the Web 2 kind of like embedding effects problem where you can't actually, like as an application developer, you don't have the sovereign data properties that your users have, I guess. And so with Abacus, we eliminate that problem. You can very easily deploy to a new blockchain, and there's no distinction of like which state is canonical. And in future, if you want to like remove a chain from your application because you don't like how that platform's been operating, or like maybe they've been the security has been compromised, you can simply remove that from your routing table, and your application will no longer accept messages from that chain. So this is an example of the ERC20. The 721 is very similar, but just to kind of like walk through it, again, we just inherit from the Open Zeppelin library, and there's one additional function, transfer remote. Same exact concept, except instead of burning an amount, we're burning a specific token ID. And then when the message is received on the destination side, we mint that token ID. And so with the 721, it's actually a little bit more complicated than the ERC20, because what we have to deal with is identifier collisions. So this is kind of like, this implementation here is, I guess, one of the like simplest approaches to dealing with this collision problem, where basically so let's say you deploy your NFT collection on N chains. During the minting period, there's nothing preventing the same identifier from being minted on multiple chains, at least in this implementation. And so our approach to solving that is basically, in this implementation, well, I guess one chain, specifically, like, I want to be clear, this is like just the simplest possible implementation we could have come up with. Minting happens on a single chain, and then later you can basically transfer those NFTs around. Something that like a use case that we're really excited about, which kind of fits nicely with the, like, I guess, gas routing policy I was describing earlier, is load balancing your NFT mint. So today, like a very kind of common problem with big NFT launches is basically they, lead to the underlying platform experiencing this like intense congestion because of like priority gas auctions, and the user experience for like users who just want to like participate in the mint is like severely degraded because the throughput of the network is limited. There's like a single pipe that all the mints have to go through, and so with Abacus, you could imagine adjusting this implementation slightly to like, instead of starting from, this is just the initialize function, so this isn't even anyone other than the deployer minting the contracts, but you can imagine like each blockchain has a specific range of identifiers that they're allocated, and minting can happen concurrently across all of those chains, and hopefully that solves the this like congestion problem where like when there's a big NFT launch on Ethereum mainnet, like the whole network's gas prices shoot up. And additionally, like this doesn't require your users to come to the specific blockchain where you're doing the mint, right? Which is a really high point of friction for a lot of these types of like, initial launches. And our thesis, or I guess like our intuition, is that ever requiring users to move chains is basically a non-starter. You kind of, I guess the ethos of Abacus is like meet your users where they already are, where they're comfortable, where they have a custody setup that they're comfortable with, where they understand the like security properties of the environment that they're on. Maybe they have some like cash in, cash out provider there that allows them to like actually conduct commerce on the blockchain that they're on. And you just expose an interface to your application, which is kind of has state across all these different blockchains. And users just sign transactions on the chain that they're on, but that can go kick off a bunch of downstream or basically remote processing logic within your application in other blockchains. And I guess I didn't talk through how transaction signing works in a lot of depth, but in line with that ethos, you don't want your user to have to sign transactions on the sending and receiving side of things. And so the way we've been thinking about, okay, so let me break that down for a second. So the reason why we are signing transactions in general to interact with smart contracts is the system needs to spend gas on our behalf. And so when we sign a transaction, we're basically authorizing miners to withdraw this amount of gas that we've specified as the limit in our transaction if they complete the computation specified in the like transaction payload. And so when you kick off a bunch of downstream transactions in other blockchains that you want to get processed from like user interaction, someone needs to pay for the gas of those downstream transactions. And so the model that we've come up with is in order to kind of like maintain this property that users don't have to move chains and they kind of only have to sign a transaction once, they actually pay gas in the source chain's native asset for all downstream messages. And we've come up with this system that we call like the Interchain gas paymaster system. I don't have a lot of slides on it because this deck is a little bit out of date, but I'd love for you guys to basically check out our docs and give us feedback on that. We just launched recently, but yeah, like basic premise is as part of the message value that you attach to transactions on the source chain, some value gets sent to this contract that we call like the Interchain gas paymaster. And there's basically these like authorized relayers which can withdraw from that contract and use the balance that you've provided for processing on the remote chains. So actually on downstream message processing, the message signer, or rather the transaction signer, will not be the same as the user's like kind of transaction origin signer. So that's just like an important thing to understand, but for the most part, when we're writing smart contracts, it's kind of like, it's an anti-pattern to care about the transaction origin. I don't know if you guys have like been writing a lot of smart contracts in your time, but in general, you want to treat users the same as you treat smart contracts. And so you want to almost always define your logic with respect to the message sender rather than the transaction origin. In any case, hopefully that approach of paying for downstream processing is in line with what you guys might expect for your user experience. There's obviously alternatives. So for example, like an application might want to subsidize all of the downstream message processing for their users, just as like a UX improvement. And so that's also possible with this system. There's kind of like a whole matrix of possibilities with cross-chain gas. This is like one we've come up with. You can imagine like far future, you could have a cross-chain AMM, which has basically these like Abacus ERC20 tokens that represent the native assets across all of the Abacus chains. And you could actually, on any chain, swap into the gas asset of the destination chain and then use that for the downstream message processing and not have any trusted actor doing basically additional like transaction relays, but instead use this native asset that you've swapped in, into through this like cross-chain AMM to basically provide like a bounty to, you can think of it as like if you guys are familiar with like keeper networks, oftentimes there's like a gas refund included in certain tasks to be completed by the keeper to subsidize their signing a transaction. And so like if you need some task performed as a application, you can just like attach this little bounty to a contract endpoint, and rather than having to operate an infrastructure layer yourself of like, hey, we need this task done, like let's poke our contract, you can outsource that by providing this like incentive to any permissionless actor to call this function, and then they get refunded with like whatever bounty you've attached. And so again, far future, far future, like you could attach this, Abacus token as a bounty, and there could be like a whole kind of like keeper network, which is conducting these downstream relays. But yeah, I guess just to wrap up, it seems like we're almost out of time. This app template that we've been keeping up to date is basically like a great place to start. You can think of it as like, your hard hat plugin, like when you do hard hat init and it creates a nice like template repo for you. This is basically that for Abacus. So if you want to get started building an Abacus application, this has kind of like a great starting place for your smart contracts. We've built a Hello World application. It's your classic like print Hello World, except it's cross-chain. And so, yeah, great place to get started. You can see kind of like all of the different layers, I guess examples of like how to work at all the different layers. We have examples of testing the system. So I think earlier I explained how to test cross-chain message handling. Here's that stubbed out function for simulating the core protocol against your hard hat node. And so, on the local contract, which is deployed on the local chain, we are sending hello world with this text, and we're sending it to the remote domain. Then we simulate the Abacus system, validators signing these messages such that a quorum is reached on the destination chain and it becomes processable. We can then basically assert that on the remote smart contracts, which exists on the remote chain, that the message has actually been received, which is just a state change defined in the handler function. So when a message is received here, we are making these state changes, and we can just assert against those types of things in our testing to kind of evaluate the boundaries of this sort of cross-chain message handling. So yeah, that's a super quick overview. I'd love to talk more to you guys about what types of applications are best suited for being built on top of Abacus, maybe after the workshop. And yeah, if you have any questions, I can maybe try and answer them really quickly, but otherwise I'm gonna probably hand it over to the next team presenting, if that's you guys. I don't know.
One question I have was about the liquidity mechanisms. Maybe something that would be helpful is to just walk through a simple usage case. I was thinking even just sort of a value transfer or a swap. What exactly does it mean to dispense with wrapped tokens and lock, unlock?
Yeah, great question. So, yeah, it would be great if we had a whiteboard or something. But yeah, with traditional token bridges, there's some canonical chain where your token was deployed at the genesis of your application. And when you want to maybe deploy your application to a new chain or even allow other chains to interact with your token, you need to basically get some of that token from the canonical chain to the new chain. The way that traditional token bridges accomplish this is there's some escrow contract that you can say, hey, transfer my tokens to this remote chain, and the circulating supply on the canonical chain never changes. Basically, the tokens just get locked up in this escrow contract, and there's some kind of protocol defined outside of the blockchain, which basically observes the escrow contract and says, okay, this amount of tokens were locked by this user or this contract, and we're going to mint it to them on this other chain. From the perspective of the canonical chain, like I said, the token supply hasn't changed. But actually on the remote chains, there is kind of now a new supply that exists elsewhere. Obviously, on the local chain, the tokens which are locked in escrow aren't really circulating, but from the contract's perspective, the supply hasn't changed from the tokens contract. With the pattern that we walked through here, with the Abacus ERC20 implementation, at least kind of the canonical one that we've been thinking about, the token supply is not defined by some canonical chain. It's the total circulating supply is actually the sum of all of the supplies on each chain. And you can freely move supply between chains. And when you do that, when you do this burn, you're actually decrementing the supply on the sending side. And so, I guess from an economic perspective, you could argue that something being escrowed or locked up and only unlockable when the tokens are kind of sent back, they're kind of economically equivalent. But I guess there's like a few reasons why we think this might be preferable. Like I said earlier, because there's no canonical chain, you don't have some fealty to like the original blockchain that you deployed on. So as long as you migrate all your supply to some other environment, now you can go and remove that chain from like your application entirely, which isn't possible with like traditional token bridging. So that's just like one property. I think we probably have to do a little more thinking about like the tokenomics of these types of systems, because there's definitely like more going on. And like, for example, if one of these like token transfers, remote token transfers, doesn't go through, now like the entire application's token supply has just been decremented. And so we have maybe like a few ways that we could have either like kind of like an ACK or a NAC type like system, which says like, okay, yeah, this transfer was actually successful, almost like a callback, which says like a promise, like, oh yeah, this was successful, or oh yeah, this failed, so that if it failed, then you could basically remint that supply on the local chain, so that there's never like totally lost assets. But yeah, hopefully that makes some sense.
Yeah, so is one of the benefits that instead of having this value locked and being sort of a credit risk into a bridge,
Yes.
that you're essentially dealing with native tokens that your bridge gets hacked, not all values.
Yeah, so Trevor, I don't know if you have any thoughts on this. This is my coworker, Trevor. I think, yeah, like there's a few different reasons why we think this is like superior to traditional token bridging. Like one reason is that you don't have like the omnibus risk of a bridge. So like when a traditional token bridge is like processing a bunch of tokens, this escrow contract is not unique to a specific application. And so there's kind of like the bounty on a token bridge is basically the sum of all of the economic value of all the applications which are leveraging that bridge. Whereas with the Abacus system, like the amount of value that you could compromise is specific to, I guess, like the amount of supply in your application on that specific chain. And there's actually like isolated validator sets for each chain. And so you can kind of like spread your risk a little bit across like different validator sets rather than like, yeah, having this like, I guess, trust and also like shared risk with all of these other applications. There's also this thing called sovereign consensus, which is kind of like an additional security layer that you can boot. And also, sorry if you guys need to, you can come set up over here.
We were here for Abacus.
Oh, awesome. Okay, cool. Yeah, so sovereign consensus is like an additional layer you can build on top. I guess like super quick rundown, like the Cosmos thesis is that like blockchains will become application specific. I think we're like in alignment with that thesis, but the problem is that in order for applications to launch application specific blockchains, they need to recruit an entire validator set to bootstrap the security of their application. And so with Abacus, when you want to like deploy on a new chain, you actually can leverage the existing Abacus validator set as like a security bootstrapping mechanism. But eventually, you can implement this thing that we call sovereign consensus, which is like almost like you can think of it as an additional veto power on top of the Abacus validator set quorum, which describes additional properties that your application uses to decide whether a message is processable. So as an example, like if you reached a certain scale as an application, one implementation of sovereign consensus could be you actually operating your own Abacus validator and requiring in your application's contract that in addition to like a economic quorum of Abacus stake being at risk attached to some inbound message to your application, you could require that the validator that you're operating has also signed that. And so there's basically like a bunch of kind of like additional layers you can strap on. I mean, it could be related to like the validator signatures, but it could also be something else entirely. Like you could have a requirement that above a certain like inbound message value to your application, you require some additional like manual oversight. So maybe you have like a trusted operator of your application on each chain, like maybe it's just your multi-sig or something, and value transfers, which are maybe like moving value out of your system over some amount. Let's say it's like $10,000 or something, or $100,000 or whatever it is. You can require basically like an additional level of security, which is specific to like the message payload. So yeah, hopefully that makes some sense. Yeah.
So how, if you want to deploy a token across multiple chains, and you wanted to maybe synchronize a bit, how would that look like in practice?
Yeah, so I guess it probably depends what you mean by synchronize. I'm being asked to wrap up, but I'm very happy to like, continue this conversation after this. So.
Yeah, is there another room? Or?
Yeah, or we can go downstairs to like the hacking area or whatever. I don't know how to remove this. Yeah.